The main purpose for this project is to understand how the steady-state error, steady-state angular velocity, and the maximum overshoot are obtained using the Matlab software simulation. So, our group managed to obtain the value while running this project, and we managed to get 5% of the steady-state error, and the target for the steady-state angular velocity, which is 14.43 radian per second. We didn't manage to get the actual value that we wanted because of some lag and error while running this project.
My name is Muhammad Zafrul Mukarita and my metric number is A164865. For the introduction, DC motor is a type of electrical rotor that converts electrical energy into mechanical energy. Most DC motors have an internal system which uses magnetism as a concept to produce energy. A normal DC motor is powered by existing direct current lighting power distribution system. The rotational speed of DC motor can be controlled widely either by changing the voltage supplied to the motor or by changing the strength of current in its field windings. We can use proportional control as means to regulate the speed of DC motor. Proportional control engineering and process control is a type of linear feedback control system in which a correction is applied to the control variable, which is proportional to the difference between the desired value and the measured value. The proportional control concept is more complex than an off-control system like a bimetallic domestic thermostat, but simpler than a proportional integral derivative control system used in something like automobile cruise control. For the objective, the main objective is to design a proportional controller that regulates the angular velocity of the motor such that it remains constant despite the presence of unmodelled dynamics, noise, and perturbations. The target specification are steady state angular velocity 25 radian per second, steady state error plus minus 20%, and maximum overshoot less than 45%.
For the literature review, Simulink is a Matlab-based graphically programming environment for modeling, simulating, and analyzing multi-domain graphical system. Its primary interface is a graphical block, diagramming tool, and a customizable set of block libraries. It offers tight integration with the rest of the Matlab environment and can either drive Matlab or be scripted from it. Simulink is widely used in automatic control and digital signal processing for multi-domain simulation and model-based design. Simulink real-time, formerly known as FTC Target, together with the X68-based real-time system, is an environment for simulating and testing Simulink and stage flow models in real time on the physical system. Another MathWorks product also supports specific embedded target. When used with other generic products, Simulink and state flow can be automatically generate sizable VHDL and Verilog.
Okay, hi, Assalamualaikum. My name is Muhammad Bishamsul Baharin, metric number GA04299. So now I'm going to present about the results and how we get the results for the Matlab for L1 model for group 20. L1 model, we need to find KT, the voltage in, the voltage output, and to recognize the order of the system, transfer function GS, and the output function CS. So first, the question provide us the formula to use, which is KT equal to V in over angular velocity as stated. So we input in the simulation is here with whatever the value that we needed to get the angular velocity, to get the KT. And then when we substitute all the values in the simulation, we get the value for KT at the tachometer reading with the value and at our report. Okay, next we need to find the voltage input where it produced 25 radian per second. So by using the same equation, we put the KT and the angular velocity in order to find voltage input in the simulation. Then we get the value of 816 voltage of input. Then the model L1 was used to find the expected voltage output by plug in the value in voltage input that we use, which produced 25 radian per second. We put it in the simulation, then the voltage output we obtain 1.762. So we put it back in the same formula, KT equal to V over omega. Then we get the tachometer gain with the 0.07048. Okay, so here's the graph. So as you can see, we take the 63% of the value from the corresponding value, which we have 1.1 volt voltage. The corresponding time is at 0.059 second. This is what stated in the theory, 63%. Okay, and for the overshoot, there are 0% overshoot, because based on the theory, the first order system does not have overshoot. So the graph here looks like this, which means it is an first order system. So since it is a first order system, we use this formula, and then at the 63%, we multiply it with the original voltage, so we get the value. Then the time, and then we use to find DC static gain with this formula first, 1 over T equal to A. And then we plug in the value, T equal to the value that we get. So we have, and then we plug in again, after we get value for A, we plug in the formula K DC equal to V times A. So we will get the DC gain with this value. Okay, now in order to calculate now we have the transfer function for the open loop. So next we need to find the transfer function for the output speed of the motor by using the formula here, CS equal to RS times GS. So we plug in all the value, and then we get that value. So we need to use Laplace inverse in order to change from CS to time domain. So we get this value, 1.762 minus 1.762 times 10 to the power of negative epsilon negative 16.94915T. So we need to find the transfer function of the output at the time T, which is from the value that we get from above. So we plug in the T value equal to 0.059. So we get the voltage output at that particular time, which is 1.138, which is similar to the one that we get, to the value that we get from the graph at the 63%. And then we put it back in the original formula, KT equal to V over omega. to obtain the angular velocity, and then we get 15.8 radian per second. So it's proven.
Assalamualaikum. My name is Wan Alif Adam, A166606, and today I will be talking about the L2 model. When our V input is 816 volts, we get the feedback voltage of 3.51 volts. Here is the Simulink model. Referring to the formula, V error is equals to the one stated here, and the value for resistance in order to have the equation of V error equals to V in minus Vt positive are when we put R1 equals to R2 equals to R3 and equals to R4. We used 3000 ohms as the resistance, and calculating the actual percentage error of the system, we get 0.37%. Now we create a closed loop transfer function. From this transfer function, we could easily reduce the blocks by using block reduction, and we get the one below. Then we substitute the value of Kt, which is equal to 0.07048, and Gs into Ts. And from there, we get these equations. Referring to the roof array and root locus analysis, this transfer function will only have a negative real roots. So Kp is more than negative 8.0526. Then we need to find a suitable Kp. We'll be using ESS equals to 0.05 as a reference. So we substitute into the formula of Kp times Gs over 1 plus Kp times Gs and Kt. From there, we could easily obtain Kp, which is 0.578 for 5% of ESS. Next, we are finding the value of Rv at a fixed value of Rs equals to 3000 ohms. So Kp equals to this 1 plus Rv over Rs, and we get the value of Rv, which is equals to negative 1266 ohms. Inserting the value of Rv into L2 model and observing the graph of actual angular velocity time response, we get this graph, and from here we get the angular velocity of 14.43 rads per second. Now we put the setting at a state error of 20% to find the desired Kp. So using the formula that I just mentioned just now, we get the value of Kp equals 0.4811 and Rv equals to negative 1556.7 ohms. So now we substitute the data, the value of Rv into the model of L2, and we get the angular velocity of 11.93 rads per second. Then we do it again, this time at a steady state error of 1% to find the desired Kp. And from here we get Kp of 0.6040 and Rv negative 1188 ohms. And using the model again, we get a graph indicating the angular velocity of 15.08 rads per second. Therefore, the best value from the three steady state errors we can get is Kp equals to 0.578 at ESS equals to 0.05, where the angular velocity is 14.43 rads per second.
Okay, now for the L3A model for our group, it is used to investigate the effect of disturbance in the open loop from the loop that we make from L1. As you can see at the simulation, there is a disturbance when t is more than 5 seconds. After t is more than 5 seconds, so we input our voltage, which is 816, and then we will get the same angular velocity as before. And then we can see that the angular velocity after 5 seconds that we obtain is 24.81 radian per second. So this means that the disturbance reduced the angular velocity by the amount of 0.19 radian per second after t is equal to 5 seconds. After 5 seconds.
As for L3B, it's correlated with L2, but this time it has a disturbance in the closed loop. So we put in the value of V in 816 volts, and R1 equals to R2 equals to R3 equals to R4 equals to R5 equals to 3000 ohms, and RV is at negative 1266 ohms and at Kp 0.578 and the angular velocity of 14.43 rads per second. And we get this graph whereby the difference in after the disturbance of the angular velocity is around 14.43 rads per second. This disturbance reduced the angular velocity about 0.002 rads per second after 5 seconds. So the final model is as stated here.
Assalamualaikum. My name is Muhammad Haidi Winos, A165756. For discussion, based on the result that we obtained from this Matlab software simulation, the steady state error that we obtained is 5% and the targeted steady state angular velocity WSS is 14.43 radian per second, which did not reach the actual value. Some error may occur during the process, resulting the difference in data obtained with the theoretical data. For example, the lack of experience and knowledge in using the Matlab software itself may cause some data error or inaccurate. Thus, some error caused by us may become one of its factors for such results. The difference of individual running the software can also be a factor for the different result. Besides that, the accuracy of tachometer, sensor, transducer, and other devices might influence the data gathering, causing the result to be less accurate and precise, as well as the system design itself, which might not be suitable for some group as the design in the model that we are assigned for the simulation. Because if we try to use our data to different group model, it will probably obtain a more accurate and precise data.
Assalamualaikum and good evening. My name is Muhammad Haris Farhan bin Shahrul and my metric number is A163756. The general conclusion from the DC motor speed control studies is that we managed to create a system to navigate the speed of a DC motor at a specific error rate. The system's component only required the three-phase supply voltage, the SCR rectifier, the DC motor and the gating circuit. This system was straightforward and does not need a design controller. This is achieved through a subsystem that we create within the design. Taking a speed PI controller as the subsystem, a much better manipulation of the armature current output was provided. By changing the proportional parameter of the controller, we were able to control the percent overshoot and the setting time of the dynamic system, which we think is the advantage of the current and speed feedback controllers. That's all from me. Thank you.